So we've learned how to approximate or actually find the exact area underneath the curve using the definite integral. Now we're actually going to take that a step further and start talking about finding the volumes of solids. And this will be done primarily in uh, three different ways because we're going to have different types of solids formed in different methods. In this video, we're going to talk about finding volumes using known cross sections, and in future lessons, we'll talk about finding volumes using rotations around an axis, which is called the disk method. And then we'll also talk about the washer method when we want to take an enclosed region in between functions and rotate it about an axis. But first things first, let's talk about finding the volume of a solid using cross sections. So take a look at this function here, y equals negative x squared plus 4. And let's say that we have an enclosed region between that function and between the lines x is equal to 0 and y is equal to 0. So what we have shaded here in blue is this is our enclosed region. Now, what I want to do is I want us to try our best to visualize this enclosed region here kind of being like the platform or the base of our three-dimensional solid that we're going to be forming. And the way that this three-dimensional solid is going to be formed is by taking one of the subintervals or one of the really tiny slivers or rectangles, if you will. So taking something like this, and let me actually just make that a little bit thicker so we can see that a little bit more clearly. So suppose we have one of our small subintervals here, and has a width of dx, we know that. And we also know that the height of one of these little kind of tiny rectangles that we have here, or thin slivers that we have here, is the value of the function at that given x. So actually, let's actually move this over here. So this will allow us to maybe do this a little bit more easily. Okay, and then let me actually also move this over here. Let's actually use this point instead. All right, so suppose we had this here. We know that the height of this is going to be whatever output we get for negative x squared plus 4, okay? Now, what I want us to do is I want to visualize, again, pretend we're looking at this enclosed region from like a top-down perspective. And one of these thin slivers here, from this top-down perspective, it's really just going to look like a line. But if we were to kind of change our angle of perspective, I want to imagine that this line is actually the top of a rectangle, specifically a square in this case. So if I were to draw like a kind of a square from an angular perspective, let me actually redraw that. It's from kind of like a different angled perspective. We would say that this here, this represents this line, that this negative x squared plus 4 is this square from this perspective. All right, we're looking at it in perspective. So if it also helps to just kind of see it from a complete side perspective, we can see that this would be negative x squared plus 4. Well, if this is a height, or this is a square, excuse me, that means the height of this square must also be negative x squared plus 4. So negative x squared plus 4. So we're looking at this from like a top-down perspective, but this is actually going to be a square here. Now I want us to imagine then that we're stacking a whole bunch of these squares now together to form the volume of a solid. And this is still pretty difficult to conceptualize. I don't have a great way of actually drawing this out, or I could. It would take me a little while. But instead, I want to actually show you this pretty neat GeoGebra widget that I found that kind of shows this. So I'm actually going to move this over here just so we can kind of see this a little bit better. So right now, I want you to imagine from our top-down perspective. So from our top-down perspective, we just see kind of a line here. But if I increase the number of rectangles now, actually, let me see what that's not really. Oh, I haven't indicated the type of cross section. So we got a square. But if I show this from a side perspective, I see that it's actually a square. So again, from a top-down perspective, it just looks like a line. But if we change our angle here, we actually see that it's more of a square from a side angle. Well, what if I increase the number of those squares? As I increase the number of the squares, you can kind of start to see what's happening here. We're stacking together an increasing number of squares. And actually, let me move this all the way over here now that we kind of see a sense of what's going on. This is just 44 squares right now. And as I increase the number of squares, we see that the heights of the squares are very much dependent on what the output of the function is. And so this is just 100 squares right now, but even from this, we look like we have a pretty firm sense of what this solid is actually going to look like. Again, from a top-down perspective, it's just going to look like I just drew a whole bunch of slivers in this enclosed region. But as I turn it over, we can kind of see that we have a three-dimensional solid. So to find the volume of the solid, what we would want to do is we'd want to find the area of each one of these squares and add them together. And now ask yourself, is there some type of tool that we have in calculus that allows us to efficiently add up a whole bunch of sums or add up a bunch of different values, find the sum of a number of values? Is there something that we have in calculus that will integrate the sum of these values? And I'm over exaggerating here, but you get the idea here. Clearly, the answer from our previous lessons is to leverage the idea of the integral. So going back to our notes, hopefully we can get a sense of how this is looking now. If we go back to our notes, we can say then that to find the volume of a three-dimensional solid formed by these cross sections, we are going to integrate the area of each one of our cross sections. Where, again, let me just kind of zoom out here, where A represents, it's a function of x. It gives us the area of each cross section. And in order to get an exact value, we need to put in our bounds. In our particular case, we want to integrate from A to B. This would be A, where we start integrating towards B. Now let's look at this in the context of this particular problem that we're doing here. So what would be the volume of the solid that is formed by the cross sections using this enclosed region as its base? Well, our lower bound in this case would be 0. Our upper bound would be 2. How would we find the area of one of these squares? Well, we just know it's one of the side lengths squared. Each side length is going to be negative x squared plus 4, and this is a function of x. Each one of these areas are going to change depending on where our x is. So we will square that side length, and this is a function of dx. Okay? All right. So hopefully that gives us a sense of how we would set up the volume using known cross sections. Really, the main things that we're going to need to know are the bounds of our integration, right? Where is this enclosed region start and end? In which direction are we integrating? And then we're going to identify what type of cross section we are using, because that's going to inform us of which area function we should be using for that problem. And if we were doing this as a function of y, that is to say we were drawing cross sections that were perpendicular to the y-axis, something like this right over here, something that was perpendicular to the y-axis. Let me make that a little bit more exaggerated here. There we go. There's that, where each one of these would be dy. All we would do then is to integrate from our lower bound to our upper bound, again, along the y-axis, but we would be integrating a of y as a function of y. And we'll do a problem like this in just a moment. All right, so let's try a couple practice problems with this, okay? Let's start with this problem over here. So let's go ahead and let's set up the integral and use that integral to find the volume of the solid that is bound by this function, y equals negative x squared plus x, and y equals x. And we're told that our cross sections are going to be rectangles with a height of 1/4 inch, and these cross sections are going to be perpendicular to the x-axis. So let's start with our graph. So I'm just going to kind of start with a basic graph here. I'm just going to sketch it. You can go ahead and put this into your graphing calculator if that helps at all. But negative x squared plus 2, actually we can do this without using our calculator. This shouldn't be too bad. So it's got a y-intercept of 2. It's negative x squared. So this is going to be our parabola. So y equals negative x squared plus 2 is going to look something like this. And then y equals x. Let me just do that in a different color. Y equals x. Well, that's going to look something like this. There's y equals x. Okay. And we see that our enclosed region is this region here. And each one of our cross sections are going to be perpendicular to the x-axis, meaning we can draw each one of these like these. So our rectangles are going to be perpendicular to the x-axis coming out towards us, each one with a height of 0.25, okay? Now, before we worry about the cross sections, let's first establish where are our intersection points. Where are our functions intersecting with one another? Well, we know that we can set our functions equal to each other to find the x values such that both functions give produce the same y. So we're just going to set these equal to each other. So we've got x squared plus x minus 2. That's x plus 2, x minus 1. X is equal to negative 2 and positive 1. Okay? So this is x is equal to negative 2. And this is x is equal to positive 1. Okay? So that's where our functions intersect. These are going to be the bounds of our integration. So from negative 2 to positive 1. Okay, so I can say that here. This is our integral from negative 2 to positive 1. Now let's establish what the area of each one of these rectangles are going to be. So let me actually just do this to the side here. So one of these rectangles here, we're told that each one of these rectangles that come out toward us, each one of these are going to have a height of 1/4 inch. Now what about the base? That is to say, let me just take this. Let me actually take this and see if I can kind of rotate it, if that helps at all. Okay, so the height is going to be 1/4 inch. So what would this be? What would this be? This would be the same thing as this here. Well, if you think back to what we did with when we found the area enclosed in between functions, we're going to want to take our higher function and subtract the lower function from it. So the higher function is negative x squared plus 2, and we're going to subtract the lower function, which is just x. So that's what it's going to be. And I can write this in descending order, negative x squared minus x plus 2. So that is going to give us the length of one of our rectangles, negative x squared minus x plus 2. And then I want to multiply this. Let me just move this to the side. I want to multiply this by the width, the length. The width is going to be 1/4, right? Length times width is going to give us the area of this rectangle. All of this with respect to x. So when we're writing this, we can just go ahead and move that 1/4 to the outside if we want. So negative 2, 1, negative x squared minus x plus 2. All of that with respect to x. And today I'm really just concerned with setting up our integrals. So you can just punch this into your calculator, although it's pretty easy to integrate by hand. But you should get 9/8 or 1.125. Oops. Let's pull that down. I don't need that. Okay. All right. Cool. Let's try the second problem now. Now, in this second problem, we're going to set up an integral to solve the following. We're going to graph a circle. So let me just graph a circle here. And this circle is x squared plus y squared plus 1, or is equal to 1. That is to say, it has a radius of 1. And the first part is going to have us find the volume of the solid that is formed by cross sections that consist of equilateral triangles, perpendicular this time to the y-axis. So if it's the y-axis, that means each one of our lines now are going to look like this, if you will. So each one of these equilateral triangles, let me actually just draw this here. Each one of these equilateral rectangles, where this is dy now, dy, okay? So in other words, we're drawing all of our lines going up along the y-axis that way. So let me just move back now that we get that. Well, the area of this rectangle, a of x, is going to be equal to, and the formula to find the area of an equilateral triangle is √3/4 s squared, the side length squared. And you can easily derive that by just drawing a height here and using what we know about the ratio of a 30, 60, 90 triangle. But what is our side length? That's what we need to establish. What is our side length? Well, the side length is going to be all of this. So to figure this out, we need to write this implicit equation as a function of x. It's y as a function of x. And when we do that, we get plus or minus √1 minus x squared. Now keep in mind, for any x value that we plug in here, depending on any x value plug in here, and I apologize, I was writing this as a function of x and I just completely forgot we're doing this as a function of y. So let me go back. Sorry about that, scratch that. So we're going to say that this is x squared is equal to 1 minus y squared. Sorry about that. It should be a function of y. So 1 minus y squared. Okay. So That means for every y value that we input, so I can choose a y value, and I'm going to get two different values of x. One positive one that would go in this direction, one negative one that would be going in this direction. So the main idea that we need to pull from this is that it's only going to give us half of this line here. So that means our s value has to be twice whatever output we get from this function, 1 minus y squared. So in other words, s is going to, in order to get this entire length going from one side of the circle to the other, we need to double whatever the output is for the function of y. So now I think I'm ready to set up my integral. So our volume is going to be integrated from -1 to 1. Again, we're moving from -1 up to +1. We're moving vertically up the y-axis. We're going to be integrating that way. Our area formula is √3/4 times our side length, which is 2 times 1 minus y squared, all of this squared as a function of y. Okay. Again, right now, I'm not too concerned about entering this into the calculator. For this problem, actually, in fact, all I want to do is set up the integrals, and this is it. If you want to, you can clean this up a little bit. We see that 2 squared is going to be 4, and that's going to divide out with a 4 this denominator, so we can actually just write this as such as well. Okay, you didn't need to, but that is an option for you. Okay, let me go ahead and make this a little bit smaller because I want to do this next part as well. Okay, all right. So now let's do the second part, which is to find the volume of the solid that's formed by cross sections that are rectangles, this time perpendicular back to the x-axis. I'm going to encourage you right now to pause this video right now and see if you can set this up for yourself. Okay, well, if you've had a chance to do it, hopefully you see that each one of these rectangles, we're told where this length here is going to be, again, this time if we write y as a function of x, we should, for the same reason that we showed over here, we should get √1 minus x squared. And again, that only is going to give us 1/2 of this line segment here, or the base or the height of this rectangle. So the same deal, to get this entire length, we need to go 2 times √1 minus x squared. And you know what? And let me actually just move this over here. Because we're told that the height of this rectangle, this height of the rectangle, is going to be 3 times that. So 3 times 2 √1 minus x squared. So I think I'm ready to set up my integral. I'm going to integrate from -1 to +1. My rectangle's area is going to be found by multiplying the base times the height, which is 6 √1 minus x squared. All of that with respect to x. And again, if you needed to, you could clean this up pretty easily, which would just make it a lot easier to integrate by hand or enter into the calculator. Okay? All right. Hopefully that helped. And in the next lesson, we'll talk about how to actually find volumes of solids that are rotated about certain axes.